Welcome back to another explainer. Today we're tackling a massive topic that trips up almost everyone when they first start deploying applications to the cloud. We're talking about mastering Kubernetes configuration and secrets. We're going to go on quite a journey today. We'll start from the absolute basic Kubernetes primitives, look at where things can go horribly, horribly wrong, and then build our way all the way up to enterprise-grade GitOps workflows and multi-cloud secret management. If you want to keep your data secure and your clusters actually running smoothly, you are definitely in the right place. Let's get into it. Okay, let's dive into this roadmap. We're going to follow a sort of good, better, best maturity model today. We'll cover the hard-coded trap, ConfigMaps versus secrets, why you should use volumes over environment variables, GitOps with sealed secrets, enterprise secret managers, and we'll wrap up with essential security best practices. Starting off with Section 1, the hard-coded trap, decoupling your code and configuration. You know, the absolute worst thing you can do is hard code sensitive data directly into your container images. But even if you do extract it, you might still fall into a massive security trap. You might think just moving an API key from your code into a basic Kubernetes secret means you're safe, right? Well, I want to start with a pretty stark reality check. Just look at this direct quote from the official NSA and CISA Kubernetes hardening guidance. By default, secrets are stored as unencrypted base64 encoded strings and can be retrieved by anyone with API access. Yep, you heard that right. If you just use the default settings, anyone who can read your cluster's underlying etcd data store, or really anyone with broad API access, can literally read your passwords in plain text. So, what does this all mean? It brings us to a really critical question. How do we actually decouple configuration from code securely? If default secrets aren't actually secret, what are our options for building a rock-solid application without leaking our most sensitive data? Well, let's start with the native solutions. Section 2, ConfigMaps versus secrets, the native primitives. So Kubernetes gives us two built-in API objects designed specifically to handle configuration. But it's absolutely vital that you don't mix up their use cases. Notice how clearly our data is separated here. On the left, we've got ConfigMaps. Now, these are purely for non-confidential data. Think of things like setting your database host to localhost for development, or maybe a cluster service name for production. They can hold up to 1 megabyte of data and can even be marked as immutable, which is a great little trick to improve cluster performance. But on the right, we have secrets. These are for your confidential data, the really sensitive stuff: passwords, SSH keys, OAuth tokens, the whole shebang. But as we just learned from the NSA, you must explicitly enable encryption at rest and strictly enforce role-based access control, or RBAC, to actually keep them safe. The golden rule here: never, ever put sensitive data in a config map, because it offers exactly zero secrecy. I really want to hammer this point home because it's such a common misconception. Kubernetes secrets use base64 encoding. Base64 encoding is not encryption. It is merely a data translation method. Honestly, think of it like pig Latin for computers. It might look like gibberish to a human at first glance, but anyone who knows the super simple rules of the translation can instantly read the original message. Base64 simply converts binary data into a string format so the Kubernetes API can handle it easily. It does not lock the data down in any way. All right, moving on to Section 3, volumes over environment variables, delivering the config, because how we deliver the data matters just as much as how we store it. Following the guidance provided by the Open Worldwide Application Security Project, or OWASP, you generally have two choices for getting configs into your pod's environment variables, or mounted volumes. Environment variables are easy, sure, but they're static. Updating a config map won't update the variable without a complete pod restart. Worse, environment variables are accessible to all processes and can easily leak into system crash dumps or logs. Mounted volumes, on the other hand, are vastly superior. By mounting a secret as a file in a read-only volume, the kubelet will actually automatically update the file when the secret changes. Plus, it keeps those highly sensitive passwords completely out of your application's process memory and environment logs. It's really a no-brainer. Let's move to how this builds into modern workflows. Section 4, GitOps with sealed secrets, the better approach. So we know how to use native secrets securely inside the cluster now, but modern development uses GitOps, meaning we want our entire infrastructure declared in code and safely stored in a Git repository. But you obviously can't commit a plain text base64 secret to GitHub, right? Enter Bitnami Sealed Secrets. This is a phenomenal tool that acts kind of like a one-way street for encryption. Here's how it works. Step 1. A developer uses a client-side utility called Kubeseal to encrypt their sensitive password locally using asymmetric cryptography. Step 2, this outputs a sealed secret resource, which is completely safe to commit, even to a public Git repository. Seriously. Step 3, once applied to the cluster, a dedicated cluster-side controller, which is the only thing holding the private decryption key, unseals it and creates a standard native Kubernetes secret that your pods can easily consume. It perfectly solves that nagging GitOps problem. But you do have to be careful here. Sealed secrets are essentially a write-only device for the developer. If you lose access to your cluster and its decryption keys, you cannot decrypt your own Git repository. Furthermore, if the controller's sealing key ever leaks, consider every single sealed secret encrypted with it entirely compromised. As the documentation warns, rotating the sealing key in your cluster does not replace the need to rotate your actual database passwords. You absolutely must do both. But what if you need centralized, multi-cloud enterprise security? That leads us to Section 5, Enterprise Secret Managers, the absolute best approach. Sealed secrets are great, but for the best approach, we need to look outside of Kubernetes itself. For things like automated rotation and detailed audit logs, we're talking about tools like the External Secrets Operator, or ESO, and HashiCorp Vault. ESO acts as a bridge. It reads information from external APIs like AWS Secrets Manager or Azure Key Vault and automatically injects those values straight into native Kubernetes secrets. HashiCorp Vault goes even further. It can actually act as a dedicated sidecar container running right next to your application pod. The sidecar authenticates with Vault, retrieves the secret, and writes it to a shared in-memory volume. Your application just reads a file, completely unaware of the complex secret management happening behind the scenes. Vault even offers a transit engine to provide encryption as a service before data is ever stored at rest. It's incredibly powerful. And using these external systems isn't just a neat feature, it's practically a requirement for top-tier security. Security agencies like CISA and the NSA explicitly recommend using an external key management service, or KMS, for encrypting your cluster's data at rest. By using a KMS provider, you prevent the raw encryption keys from ever being stored on your cluster's local disk, closing a major vulnerability gap. So the crucial point is how we bring all this together. Section 6, Essential Security Best Practices, locking it down. Whether you use native secrets, sealed secrets, or HashiCorp Vault, the surrounding cluster security has to be incredibly tight. Let's rapid fire through the core guidelines laid out by OWASP and federal agencies. First, enforce strict RBAC. Specifically, you have to restrict watch and list permissions on secrets. If a subject can list secrets, they can read every single secret in that namespace, not just the ones for their specific app. Second, isolate access using Kubernetes namespaces. Third, automate your key and secret rotation. Do not rely on human memory for this. Fourth, absolutely avoid running containers with privileged equals true, because a privileged container can literally access all secrets used on that entire node. And finally, implement comprehensive, centralized auditing and logging, so you know exactly who or what accessed a given secret. Least privilege access is absolutely non-negotiable here. We have covered a lot of ground today, from the real dangers of base64 encoding to the elegance of sidecar injectors and external KMS providers. So, I want to leave you with this final provocative thought. When you go back to work tomorrow, really look at your infrastructure. Are your cluster secrets truly encrypted, or are they just hiding in plain sight? Take the time to audit your configurations, move those configs to mounted volumes, and implement a true secret management strategy. Thanks for joining me on this explainer, and